So thank you for the introduction, and thanks to the organizers for having me here. I'm very happy to be here. And I will actually talk about a joint project, or actually a series of projects together with Marco Cicalese in Munich, Gianluca Orlando, who's now in Bari, and Leonard Kreutz, who's now in Pittsburgh, and which is about the antiferromagnetic XY model on the triangular lattice. So we have already seen the antiferromagnetic XY model in the talk by Michele. I'm a bit sorry, I prepared a kind of introductory part about the XY model and related topics, but now during the workshop we have already seen the related models at least a couple of times, so I can be maybe quick on that. So, but just to set up the context in which we are working, so we are given a small parameter epsilon greater than 0, and we are considering configurations which map from the epsilon space square lattice for the moment. We will later go to the triangular lattice contained in a domain omega to the sphere S1. So to every point in the lattice, I assign a direction in S1. Then on these configurations, we are considering an energy which is just the pairwise interaction energy. So I'm considering the sum of our nearest neighbors interactions, which are just the scalar product between my two neighboring vectors. I am multiplying with the volume of the unit cell, and then I will weight this with an alpha, which can be positive or negative. Okay, so we have an energy, we have can look for ground states, which of course will depend on the sign of alpha, as we have seen before. So if alpha is greater than 0, obviously, so where is my pointer? Here. If alpha is greater than 0, then of course you want to align your neighbors to minimize your energy. If instead the alpha is less than 0, you would like to make this scalar product as small as possible. So you want to put antipode on nearest neighbors, and we've already seen in the talk by Michele that you can really realize that on the square lattice. So you can minimize all the pairwise interactions to get a global minimizer. Of course, this energy has a feature which is the invariance under global rotations, which is also referred to as S1 symmetry. So every rotation of this ground state will be another ground state, similarly here for the paramagnetic model. Okay, so, but maybe you're not only interested in ground states, because maybe you want to prescribe some boundary condition on omega of Dirichlet type, or maybe just a degree condition, which prevents you from putting everywhere parallel vectors or everywhere antipodal vectors. So actually, what is the general goal in this framework, let's say, is to understand the asymptotic behavior of so-called low energy states, and I will be a bit more precise on that in the next slide, as your lattice spacing goes to 0. So somehow you want to pass to a macroscopic continuum model, and you want to understand the asymptotic behavior in a certain sense of configurations which are not necessarily minimizers, but close to minimizers in some sense, and that's what I will be more precise about now. So what do I mean with low energy states? So those are configurations which can deviate. So okay, one disclaimer. I'm doing everything for simplicity now on this introductory slide for the ferromagnetic XY model, and for simplicity I put alpha equal to 1. But in general, you consider configurations which, or sequences of configurations whose energy can deviate from your minimum value by a certain amount, eta, let's say eta epsilon. And this eta epsilon will go to 0 with epsilon. So of course you might ask which scaling eta epsilon is meaningful, and this is already part of the problem, let's say. So meaningful means you would like to choose your eta epsilon in such a way that for energy satisfying this energy bound, configuration satisfying this energy bounds, you can get compactness, maybe not of the field itself, but of certain quantities depending on your u epsilon. And once you have that, well, you have a compactness result, you would like to couple it with the gamma limit result, and this is what I mean with asymptotics. So I would like to take the gamma limit of now this quantity divided by eta epsilon, which I detected as a meaningful scaling. So believe me, this is just, I mean, we saw here essentially if you put always parallel neighbors to K1, so this is a 1 minus 2i. So let me give a name to this guy, which will, from now on will be my XY energy. So we would like to pass to a continuum model. To this end, it's very convenient to actually use that you have unit vectors. So you can rewrite this scalar product here as a square. Just expand the square, you will see that you end up with the left-hand side. Well, of course, now you have here like finite differences. So you can take a piecewise affine interpolation on a triangulation subordinated to your square lattice. You see that this one is for the piecewise affine interpolation up to some errors on the boundary is exactly the Dirichlet energy. You have something more. So of course your piecewise affine interpolation now is not anymore an one-valued function, but you can control somehow, you can control with your energy the deviation of your field or your interpolation from being a unit vector. So now if you see those two terms, well, we have already seen the Ginzburg-Landau energy a couple of times during this talk, so if you sum those terms up, you get the Ginzburg-Landau energy. And this was an observation already made in 2009, that actually, so I already put a certain rescaling here. So actually, if you rescale by epsilon squared log epsilon, then your XY model energy behaves like the Ginzburg-Landau in the logarithmic rescaling regime, which is this guy here, which means, well, this is nice because the Ginzburg-Landau energy was studied before, and you also, this is another meaningful scaling. So the Ginzburg-Landau energy, as I said before, I mean, they have been studied from different perspectives. I'm sure I'm missing some references here, but just from a variational point of view, you have properties and asymptotics of minimizers, you have lower bounds, and you even have asymptotics via gamma convergence. Of course, so then the key observation here is that for the Ginzburg-Landau energy, whenever you have a sequence, let's say now in the continuum of fields in H1, whose energy satisfies this logarithmic energy bound, then you know that the Jacobian, which for these H1 functions can simply be thought of as the determinant of the gradient, they converge in a flat sense to a measure, which is a sum of Dirac masses centered in points in your domain and with some integer weights in set. So similar to the multiplicity that we saw in Adriana's talk before. Okay, and for the moment I will not go into detail what is the flat convergence here. Just think about something which is weaker than weak star convergence, because you only test with Lipschitz continuous functions where the Lipschitz constant is bounded by 1. Okay, so of course, since you have this result for in particular this compactness result for the Ginzburg-Landau energy, and you have the bounds on the comparison between the XY and the Ginzburg-Landau, once you know that you have a discrete configuration now which satisfies this energy bound, so epsilon, the eta epsilon in our setting would be epsilon squared log epsilon, then you know that now the Jacobians of the piecewise constant interpolation, they will converge flatly to such kind of measure. And moreover, you get the gamma convergence result relying on the corresponding gamma convergence result for the Ginzburg-Landau, which tells you that in this logarithmic rescaling regime, you will gamma converge to something which is the total variation of this limiting measure on omega. Okay. So this was the maybe a bit abstract. Let me just give you some concluding remarks, and let me tell you what are typical configurations. Actually, we already saw some of the computations already in the talk by Adriana. So during this week, I was just listing things that have already been said, and now Adriana just added a few new things. So typical configurations, let's just think about a limiting configuration where you just have a Dirac measure, let's say in 0 with weight 1. So a typical configuration, which actually gives you the lim sub in this case, would be the discretization of x over mod x. I put the rotation here just because it's more pleasing. And well, this one will actually scale like, let's say you will be here in a ball with radius r. Well, this is nothing up to in the leading order, then integrating the gradient of x mod x. This is a direct computation. You see that this is high log R, as we saw in the talk by Adriana before, and this actually also tells you why the logarithmic rescaling is the meaningful scaling. Of course, this is a particular configuration. You can go further and say that whenever you exclude, let's say, a ball with the radius r, small r, and you take the infimum among all h1 functions which have satisfy a degree condition on the smaller ball, which is of course okay. You should take x to divided, so x mod x to the power d. So you take the energy, Dirichlet energy on this annulus. Then this will go quadratically in the degree, and you will have a factor which goes like the logarithm of the ratio. It's the computation that we saw essentially before by Adriana. Okay, just to give you an idea what will typical configurations look like. Let me just wrap up that in this energetic regime, we have that low energy configurations develop finitely many singularities, and the quantity which tracks these singularities is the Jacobian of the piecewise affine interpolation. You can use other things to track it, and we will see it later, because actually you can define it in a discrete setting, the Jacobian. But for the moment, take the Jacobian of the piecewise affine interpolation. And we've already seen that well, the XY model behaves like a Ginzburg-Landau model in the piecewise affine interpolation. Let me just point out that there is another connection, which is if you take now the angular lifting of your exponential function, so if you of your S1 valued function, you can relate the XY model to the screw dislocation model in this angular lifting. So what do I mean with that? So if I express my u as the exponential of 2 pi I phi, then the XY model behaves essentially like a screw dislocation model, where here, this is, if you want, the elastic energy, so the square of the elastic part of a gradient. But I think Adriana will tell you more about that. So, which is a connection that has also been observed in a series of papers. And let me just finish with the picture that in the screw dislocation context, while this would singularity here would again correspond to an extra line of atoms coming into your lattice here, like we saw in the talk of Adriana, except that now it's screw and not edge. But okay, so if there are no questions so far, I think we have like the context on which we can build, and I would like to state now really the model that we are studying, and which we studied in these two papers up to now, and which is the antiferromagnetic XY model again. So this was ferromagnetic, but let me just stress that on the square lattice there's not such a big difference between the ferromagnetic and the antiferromagnetic. So there's a change of variables with which you can go from one to the other. So this changes if you go to the triangular lattice, and yes, I will be more precise on why. So, as a reminder, this is the square lattice, but from now on I will consider the antiferromagnetic XY model energy on the square lattice, and for simplicity I take alpha equal -1. So this is our energy. And just as a reminder, these were like your nearest neighbor interactions that you would take into account on square and triangular lattice. Of course, we saw already that on the triangular lattice you can minimize all interactions pairwise to get a global minimizer. So this obviously changes when you go to the triangular lattice Y, because well, you can try to try to do your best. So you start with one direction and let's say I. You try to put the antipodal neighbor in J, so to make this interaction happy. And then of course the K doesn't know what to do, because can obviously not be antipodal to both I and J, and it's the nearest neighbor of both I and J. So it's frustrated. That's what we call frustration, if you cannot minimize all the pairwise interactions simultaneously. So, well, you are left with a conflict. You should find a compromise. And to understand what this compromise is, it's again convenient to write this scalar product as a square. If again expand the square, you will see that you end up with that. So now, and I'm rewriting as a square on triangles. But this is ijk. So now, of course, this term is always positive. But it becomes 0 if your vectors sum up to 0. So in some words, if they close the triangle. So if you always rotate by 2 pi over 3. Well, and then you see that you can actually decompose your lattice into 3 sublattices, and you can put these vectors on your whole domain according to the sublattice to which they belong. And you get a ground state. And as I said before, we have S1 symmetry, so of course every global rotation of this ground state is another ground state. But there's another symmetry in this model, which is usually referred to as the Z2 symmetry, which is you could swap these two vectors in J and K. So instead of rotating by 2 pi counterclockwise going from I to J to K, you rotate counterclockwise. And this gives you another ground state. And this obviously cannot be obtained from the previous ground state by a global rotation because it's a permutation of odd sign. So this gives you another family of ground state. So now there's a variable which distinguishes between these ground states, which is the so-called chirality. So I wrote the definition here, but don't think about it too much. Just keep in mind. So this is a, let's say, a variable which depends in a nonlinear way on u, and it takes values in -1 and 1. And roughly speaking, it distinguishes if you are in the sublattice, you go from I to J to K, you rotate clockwise or counterclockwise. So if you rotate going from I to J to K, counterclockwise it's positive, if it's the other way around it's negative. And it is equal to 1 and -1 exactly on your ground states. Okay, so far so good. So now the goal is, as before, you would like to investigate the asymptotic behavior again in terms of gamma convergence of this energy, which is up to a factor 2, the one here after removing your constant, which corresponds again to the minimum value. Okay, so this is the energy that now we would like to consider. So from now on, whenever you see f epsilon, this is what I want to consider. And just as a remember, so on every triangle, so this means I localize the energy to a triangle, this energy is 0 if and only if chirality is equal to plus and minus 1. Okay. Any questions so far? No. Okay, then I can go on. So to get obviously, in particular, to get asymptotic lower bounds and to get compactness, it's good to get energy barriers. So energy, and in particular, we're interested in energy barriers in neighboring triangles for certain configurations. So let's take two neighboring triangles, T and T prime. And let's suppose that my chirality switches sign in those two triangles. So here ijk, I go counterclockwise, here ijk, I go clockwise, so I switch the sign. Here plus, I have negative chirality. So it turns out that's a direct computation that then on the union of these two triangles, you pay a fixed amount of energy. Which is, okay, now multiplied by epsilon, because epsilon squared, because this is the volume scaling here. Okay, this can actually be made continuous in some sense. So let's suppose that now I don't switch chirality, but let's say here I'm actually close to a ground state of chirality 1, also here. But now here I'm obviously far away from a ground state. So let's say it's a bit sloppy here, but here I'm close to chirality. Chirality is close to 1. It's not anymore close to 1. Since I have this property here that my energy vanishes if and only if I am close to my chirality is plus or minus 1, I know that also here I pay a fixed amount of energy when now this constant, well, it depends on the threshold that you fix here of being close to 1 or not close to 1. But still, you get something. Okay, let's focus a bit on this property here. What does it tell you? So it tells you that if now I consider a sequence U epsilon and I let A epsilon be the set where my current is positive, then this is obvious. I mean, it's a union of triangles. And I can bound the Hausdorff measure of the boundary of my triangles, of my A epsilon, with, well, the length of the side length of a triangle times the number of the boundary triangles. Well, if I use this estimate, I can bound this again by my energy in this way. So I get in 1 over epsilon here, which tells us that there might be another meaningful scaling in contrast to the square lattice. We don't have this additional chirality variable. So let me just wrap up. So this is what we have seen so far. We can bound the Hausdorff measure of the boundary of the characteristic set where the chirality is positive by the energy divided by epsilon. And well, this characterization we probably saw before. Well, this seems a bit like, not exactly, but this seems a bit like an easing system in the chirality variable. Obviously not exactly, because the chirality takes variable values in the whole interval -1, 1. But it's minimized, so the energy is 0 if and only if we have plus and minus 1. And well, you know that for easing systems there happens something on this 1/epsilon scaling regime. So, and this is exactly what we were able to prove. So if your sequence u epsilon satisfies an energy bound which goes like this, so you are allowed to deviate from your ground state by an amount of epsilon. You already have a meaningful scaling. You get that the up to subsequences, your chirality will converge to a BV function which takes values only plus and minus 1, so exactly your minimum values. Well, BV function have already been introduced before, but in this case it's if you want partition function and taking values -1 and 1. And moreover, you can prove a gamma convergence result. You can see that in this rescaled regime, your energy is actually converged to surface type energy, which can be expressed in terms of the chirality variable. And I'm not giving the formula for phi here, but it's an asymptotic cell formula, as we have seen before in the talk of Katharina or also Adriana. It's a bit tricky here to prescribe boundary conditions because you have this S1 symmetry. So you would like to prescribe the boundary condition in the chirality, would be natural, but then you have any possible rotation of a ground state. So this is not what you want to have. You need to fix your field, and this is a bit a mess, but it can be done. So let me just, as a remark, say that you see the transitions in the chirality, not in the spin field. And that's also why, so on the square lattice you don't see an effect like this because you don't have a chirality. So, and indeed, so what you can think about is that for small epsilon, your domain will be partitioned into several regions where you might have chirality. So you should have, let's say, configurations where the chirality is close to 1, and on the other part, chirality is close to -1, but they might rotate. Of course, you would like to understand something more about this possibility of rotating. So the question is, what happens if now our energy, so we take configurations which are allowed to deviate from the ground state by a less amount of energy to something which is going to 0 faster than epsilon. So for example, the energy bound epsilon squared log epsilon. So this one is of lower order. Well, obviously, in this case, you cannot overcome the energy barrier to perform a transition in the chirality. So your limiting chirality will be either constant to 1 or constant to -1. So let's assume for the moment that we converge to 1. Can we say something more about our fields, u epsilon? And well, actually, what you would like to do is you would like to compare your energy with the ferromagnetic XY model energy on the triangular lattice. So in the introductory part, I used the square lattice because that's where everything started, but actually also on the triangular lattice, the XY model energy has been considered. So there's the paper by Lucia de Luca about the XY model ferromagnetic on the triangular lattice. Okay. Well, so from now on, I will always assume that my u epsilon is a configuration that deviates from the ground state by amount less than epsilon. So we will see the epsilon squared log epsilon, but we'll also see an epsilon squared. So this is in general, these are the sequences that I'm considering from now. And in addition, I'm assuming that my chirality converges to 1. Okay. So what you would like to do is you would like to transform your antiferromagnetic XY model into a ferromagnetic. So you start from a ground state with chirality T1, and obviously you would like to transform this set of vectors on the triangle into a set of vectors which is a ground state for the XY model, so ferromagnetic. So you wouldn't like to transform it into a set of parallel vectors. So let's say we fix one sublattice I, and we keep the vector here. Then on the J sublattice, we will always rotate clockwise by 2 pi over 3. On the K sublattice, we will always rotate clockwise by 4 pi over 3. Okay, so this obviously transforms ground states of chirality 1 into ground states for the XY model energy. You can also do that globally. It's well defined. You can do this transformation globally, but you need to pay attention. So this is fine if your chirality was also before, let's say, at least close to 1. Then you know that you can compare the two energies. You can compare your energy F, so the original energy in U epsilon, the antiferromagnetic energy in U epsilon, you compare it with the ferromagnetic XY and the new variable which is denoted by V epsilon. That's fine, but, well, something really bad happens if you have had before a chirality -1. Remember, if I have a chirality -1, I paid 0 in my original energy. But it actually turns out that in the ferromagnetic XY, you pay a fixed constant. It's easily seen, because what happens if you do this change of variables on a ground state with chirality 1? Well, actually you end up with the ground state of chirality, -1, you end up with the ground state of chirality 1. And obviously this is not a set of parallel vectors, so I think you believe me that here you pay a fixed amount in the XY model energy. And okay, I wrote it here for chirality being -1, but obviously you have a problem once you're close to -1. And you cannot exclude it. On the epsilon level, you cannot exclude that there are triangles where you have chirality -1. You just know that in L1 your chirality converges to 1. But obviously on the epsilon level, you have to deal with the situation. So you actually want to estimate the region where your chirality is not close to 1. Because in the chirality region close to 1, you're fine. You can use this comparison. If this is not satisfied, well, you have a problem. So let's try to estimate this region. We have already seen this estimate in some sense before. At least the picture was there before, but now I'm considering a set A epsilon to be the set where my chirality is not close to 1. Let's say I fix the threshold lambda and I say here I'm less than 1 minus lambda. Then we have seen with the same argument as before, you remember that I said this argument of neighboring triangles where you switch chirality, where your chirality switches sign can be made continuous. You have an energy barrier on neighboring triangles. When in one triangle your chirality is close to 1 and the other it's not. So with the same argument you can bound again the Hausdorff measure of the boundary of your set by your energy. You also know that your chirality converges to 1. So this should actually be, let's say, the minority phase. So you can actually apply an isoparometric inequality, and you can see that the back measure of the set can be bounded up to a constant by the Hausdorff measure squared now. And it's a bit bad. We were a bit desperate at some point that we got a square here, but that's what the isoparometric inequality tells you. And this goes now, but using that estimate like that. So here you have your energy squared. Still, we were assuming that this one is negligible with respect to epsilon. So it goes to 0, and you actually have a rate here, which depends on your original energy, but it goes to 0. However, so let's assume for the moment that our original energy was allowed to deviate from the ground state only by an amount of epsilon squared, which is not really the thing that we wanted to consider, but then our XY model would satisfy so the ferromagnetic in the transformed variable would satisfy the same energy bound. So also would be less or equal than C epsilon squared. If now, okay, and also, well, you can compare in the rescaled setting the energies, okay. But if now you were allowed from the beginning to deviate from the ground state by an amount of epsilon squared log epsilon, well, this square is really bad because it gives you an epsilon squared log epsilon squared in the XY model. So now for people who know the XY, the literature about XY or Ginzburg-Landau a bit better, they will see that these a priori are really bad news, because for general fields satisfying this energy bound, you would not expect any more concentration on points. So you would lose this property. And instead, your rescaled Jacobians, they might become diffuse. They only might converge to a measure in h-1, and you will actually see what Adriana was mentioning before. You would see the far field energy, and which is known in the context of dislocations as the strain gradient models, while the concentration on points or lines would be the line tension model. So this would be like a completely different setting. So at some point we were really confused and we thought like, okay, do we need to go to a different regime? But obviously there is something more that we know. We know that if we are outside of this bad set, well, we have a good energy comparison. And we still know, so we still know that the disco one goes to 0. So you need to remember that this is not a general field W epsilon, but it comes as a transformation from another field, and you need to use those properties to conclude and to let's say circumvent this difficulty here that you don't have the optimal lower bound. Okay, I think I'm in time. Yes, so let me just say that this was actually enough, and I will give you more details why, to prove the following results. So we have actually two results, one in the bulk scaling and one in the more interesting, the vortex scaling. So if your U epsilon satisfies the stronger energy bound, and your chirality converges to 1, then, I mean, it was already almost there on the previous slides. Then you have that up to subsequences now, the piecewise affine interpolation of your transformed field converges in H1. Converges in L2 to a function H1. And your rescaled energies, they gamma converge to the Dirichlet energy multiplied by a factor which comes from the volume of your unit cells. Okay, and well, the strategy to do that is really to use the quantification of this measure of A epsilon, which tells you that in this regime you can really have only finitely many triangles where you cannot compare your antiferromagnetic with the ferromagnetic, and you can deal with that. Finitely many triangles, it's easy to explain. If instead you are in the vortex scaling, so if your energy satisfies this coarser energy bound, and you still have that the chirality converges to 1, you still get that up to subsequences, your discrete vorticity measures, which up to now I didn't define, but think about the Jacobians of the piecewise affine interpolation for the moment, they converge again flat to, I think I missed the pi probably, to a measure of this form. That we saw before. So the sum of Dirac masses centered at points in your domain and with integer weights. So it's actually the same scaling as, so the same type of concentration on singularities as we saw for the ferromagnetic XY, although we don't get the optimal energy bound for the ferromagnetic in the transformed variables. And you also get a gamma limit result. So the rescaled functionals, they gamma converge to, again, the total variation, essentially of this measure now multiplied by a different factor, which corresponds to the one here, so comes from the volume of the unit cell. And so the strategy in this vortex scaling regime then was, well, actually to exploit what you get from the bulk scaling on annuli, a bit like we saw again on the talk of Adriana before, so annuli are always nice to consider, and to use the ball construction, which was already around before. And if there are no questions so far, since I think I still have a bit of time, are there questions so far? No. Then, since I think I still have a bit of time, I will try to tell you something more about these discrete vorticity measures and well, how to circumvent this bad energy bound, let's say. So let me give you some ingredients of the proof, at least. So we saw before that we can, in principle, take the Jacobian of the piecewise affine interpolation. But if you really need to put hands on, it's nicer to define something, a discrete vorticity measure, let's say. I'm cheating, I'm not really giving you the definition. But so your discrete vorticity measure will be, again, some of the Dirac masses centered now in the very center of your triangle, and the weight that you put is either -1, 0, or 1. And essentially, I mean, you distinguish between the situation where you cover as one counterclockwise or clockwise, maybe clockwise or counterclockwise, or not. I mean, if you think about, you would interpolate here, you would get a degree or not. So you get -1, 0, 1. If you want to see the definition, I could use the blackboard, but if you're fine with that, you will stay with it. Okay. Let me just say that one important remark, which might be confusing, is that the chirality that we saw before, it distinguishes somehow between upwards and downwards facing triangles, because it remembers the sublattice. You always go I, J, K. So going from I, J, K, I to J to K, let me just because I removed everything. Let's say here was I, J, K, and my sublattice, and let's say here's an I prime. So the chirality, I would always go I, J, K, and I would say, do I go clockwise or counterclockwise? I, J, K. But with the vorticity, I always go counterclockwise. So I would go like this, and I would go like this. And this will become important later. But also to tell you that those variables are really something different. Okay. Let me also mention that you can actually construct a suitable interpolation of your transformed variable v, which satisfies this equality. So the Jacobian of this interpolation, now defined in the distributional sense, coincides actually with your measure up to factor pi. Of course, here this is not the W12 function, it's only W11, but you can still make sense of this out of this in a distributional sense. And in particular, you can use that to get a nice lower energy bound on annulize, where you say that your measure in a small ball should be equal to certain integer d, and the mass on the annulus is 0. Then you can actually pass to the continuum. You use the bike scaling, you can pass to the continuum. You need to transfer this mass condition to the degree condition, and you can use the energy bound that we saw before from Adriana, and it was already there on the previous slide to see that this goes like the square of the degree and the logarithm of the ratio. Okay, just as a side remark. And maybe the most important thing to keep in mind about this vorticity measure is that actually you can bound your total variation of your measure by the XY model energy. This is, I think, immediate. Okay, and this is usually used to get compactness. So of course now here we don't have the optimal energy bound. So how do we still get the required compactness on this measure? And well, maybe for that I go a step back, and probably this question is stupid for a lot of people here, but you might ask yourself, why do you need actually the flat convergence? This is a recap that these are the energy bounds that we have. So let us assume for a moment we could match the required energy bound. We don't have it, but let's assume for a moment that we had it. We saw in this, let's say, cartoon computations that typically these configurations, which have the plus here, the positive vorticity here, discrete vorticity here, if they continue like this, they pay like the logarithm of epsilon already. So you might ask yourself, why can't I get it? This one is uniformly bounded, and I could use a weak star conversions, well, because this is a local picture, and you don't know how this continues. So you can actually, you have something, you have these short dipoles which eliminate itself. And now if you actually go around here, you will see that you don't get a degree anymore. So short dipoles actually lead to cancellations on mesoscales, and you don't pay the full logarithmic contribution. So to pay the full logarithmic contribution, you need to extend this to go on to a macroscopic analysis. So then, of course, and this is, I think, the key idea of the ball construction, what you would like to do is you would cluster those, discrete singularities. You would like to take a ball containing both of them, and you would like to define a new measure which is, let's say, concentrated on the center of the ball, and which has the weight, which is just obtained by summing up all the weights of your original measure. Well, of course, you don't know if it's good to stop here, or if there are other discrete singularities close by that you should also include. So you should make this ball even a bit larger. But this is something that can be made rigorous by the ball construction. So essentially, you start with a collection of disjoint balls, and you let them grow linearly until they meet, and you merge them. And you need to find a nice point where to stop, so that you have two things that you measure, let's say mu epsilon tilde, that you construct in this way. So on the one hand, satisfies an energy bound like this, so has bounded total variation, and at the same time converges to the same flat limit as, so the difference between your original measure and the modified measure converges to zero in the flat sense. And this is typically granted, so you can find this nice stopping time, let's say, if you have the logarithmic energy bound. That we don't have. But let me conclude by saying that although we don't have it, we almost have it in the following sense. So actually what you realize that the bad situation is when you have two neighboring triangles where close to chirality -1. Now here I depicted it with chirality -1, which you will immediately deform into a very short dipole. Let's say you get plus vorticity in one triangle and minus vorticity in the other triangle. So as a take-home message, so the log epsilon squared many vortices, which seem to be bad, they actually appear only as, let's say, very short dipoles, and they get killed instantaneously in the ball construction. And then you're in busyness, and you can more or less apply the ball construction as you're used to do. Well, you get to the compactness and the gamma limit. So the compactness is more or less the idea that I sketched before. For the gamma limit, well, you follow the ball construction actually, and you collect your singularities until you get a lot of balls where your sum of all the weights is zero. So here essentially you kind of exclude them by showing that you can extend inside the ball your field to a Sobolev function without degree. And then on these remaining finitely many balls, you actually consider annuli around them with radius which go like exponentials in epsilon, and you exploit bulk scaling on these annuli. Okay, and I think with that I close. I give you a little summary of what we have seen. So we have seen the asymptotic of the antiferromagnetic AFXY model. In gamma convergence, we have seen that on the surface scaling, we have the chirality variable, which detects, let's say, the interesting features, so where we can get compactness and with which we can express a gamma limit, which is of surface type. And we have seen the energy concentration on the vortex scaling, which can be seen in the vorticity measure if you want the discrete Jacobian of a transformed field. For those, we have seen that there are finitely many point singularities which appear, and all those energies store the finitely many limiting singularities, they store an energy of order log epsilon. And well, okay, let me close with some pictures. So let's say this is somehow how your V should look. So the transformed variable should look like around the limiting singularity. So now if you retransform your field, this is somehow how your U looks like. It looks a bit chaotic at the moment. But if you look only on the sublattice that we didn't modify, you see that actually you have somehow a vortex here. And if you focus a bit on the triangles, you see that actually what I said before, maybe in the middle of the talk, that you really rotate the ground, like something which is close to a ground state around the limiting singularities. And with this, I think I stop, and I thank you for your attention.